Hi, everybody. Very good. Giorgia, is it okay if we record?
Yes. Okay.
Sorry, I just sprung that on you right now.
Yeah.
These end up on an obscure channel on YouTube, if maybe like 50% of the time.
Okay.
If that's okay.
I'm trying
It's
to.
actually,
I can't. I try to minimize the thing here, but I lost my cursor.
oh, you lost your cursor.
I mean, I can see things moving, but maybe if I click, something happen. No. But,
I see page 2 now.
okay. Yeah. Okay. Whatever. Fine. I'll just leave it like that. No, just the list of participants. I don't manage to minimize it, but that's fine. So,
Okay, everything's fine from our end, so we're good.
okay.
Good to go. Oh, hello, everyone. We're very pleased to have Dr. Giorgia Busso from University of Cambridge. We talk about the Gaia mission. She's a senior research associate there. And this is Cambridge, England. She got her PhD in 2007 from the University of Kiel. And then, but pretty soon thereafter, got involved with the Gaia mission. So she's on the Gaia team. She's on like every Gaia paper, the collaboration. So it's really, really nice to have an update on Gaia and some also perspective for the near future when data release 4 comes out. So thank you very much, Giorgia, for joining us. And
Okay.
we can hear you and see you just great. So go ahead and begin.
Thanks. Hello, everyone. Thanks for inviting me. Yes, I'm a Deepak member for I don't remember how many years. So really, yeah. Well, started to work on Gaia before launch. So it's I'm not an expert because Gaia is so complex and there are so many things that it's really impossible to know everything. So I'll try my best to navigate navigate you through this talk. So yes, I'm going to if there's still someone that doesn't know this guy, I'm going to give a brief introduction to the mission, and then some information about the last data release that was data release 3. And I mean, as I say, Gaia that has been used in almost in every astronomy astrophysical field. So the results are just too many. So I just pick a few and just to show you the span, how wide is the range of science that Gaia can do. And then you are very lucky because I'm going to give you a sneak peek into DR4 and lately at the end talking you about the last data release, DR5, and what hopefully will happen in the future. So Gaia was launched in December 2013. So yeah, in a month, it's almost 12 years from on a Soyuz rocket. Here you have an image of the Gaia satellite. It's quite big. It's as big as a Alpha tennis court, more or less, just to give you an idea of the size. And it was launched in December 2032 and was put in orbit around L2, the Lagrangian point L2, where there are many satellites there. And I think the Webb satellite is there, Euclid I think is there as well. And L2 is the balance point in the one of the balance equilibrium point in the system Sun, Earth, and Moon. And what Gaia does is follow the Earth in orbit around the Sun. And this is important because Gaia, one of the main aim of Gaia is measuring the distance of the stars, and to do this, use the parallax method, that is measuring the angles between close stars and further away stars. And using the orbit of the Earth as a baseline give us we can measure angles so small that it can give us a very a great accuracy in the measure of the angles and then of the distance of the stars. So on board there are three instruments. So an astrometric instruments, they have astrometric field, which basically collect the light in white on the G band, which is basically white light. There you can see the plot with the wavelength bands of the instrument, and the G band is the green one. And then there are also two spectrograph on board, one to do spectrophotometry, and it's a low resolution, and another one is to measure radial velocity at higher resolution. There you see also pictures of the Gaia focal plane, which is basically a mosaic of more than 100 CCDs that are working on in TDI mode. Yeah, here, yes, as I said, the two spectral, there are two low resolution spectrograph on board, which are basically two prisms, and one in the blue and one in a red band. So they are called blue and red photometers, which in short is stay for BP and RP. And even if they are very low resolution, we are still able to distinguish the different spectral types. Here, you have an example of the BP and RP spectra for, yes, as I say, different spectral type. And the integrated fluxes of these spectra is what gives you the BP and RP magnitude. And then there is the high resolution spectrograph, it's called RBS, radio velocity spectrograph, much higher resolution, that observes in a smaller range around the calcium triplet wavelength range. And here you can see an example of an RBS spectrum where the calcium triplet and also other lines are quite visible. And this is to measure this triplet is the one that is used to measure the radial velocity of the stars. And yes, as I said, the main aim of Gaia is to make 3D census of the Milky Way, because then we can measure the position of the stars, we can measure the distances. From the photometry and the low resolution spectra, we can measure, we can distinguish the type of stars, and we can also, since we are Gaia scanning continuously the sky, we can measure also the proper motion of the stars and the radial velocity. So actually, more than a 3D census is a 6D census of the Milky Way, because we have to keep into account also the motion of the stars, not only the positions. And to do that, yeah, as I say, Gaia scan continuously the sky. Here you have this animation show you how the observation principle of Gaia. So Gaia follow the Earth around the sun and observe at the same time. I should have, let's see if I forgot to mention that here. On board Gaia there are two telescopes, trailing and leading a trailing field of view, and that so observe at the same time the two field of views. The two telescopes maintain a fixed angle. It's called, yeah, the basic angle. So, and so moving along the ecliptic, Gaia scan the skies, covering all the sky, and is okay. Now it's going to speed up. Hopefully, yeah, here. And basically, it covers the whole sky. Gaia covered the whole sky in 4 months, and considering that Gaia has been observing for 10 years, you can imagine that how many times the number, the stars have been observed. Okay, this animation arrives, I think only until no, I think until the end of the nominal mission, so 5 years, and the color scale gives you the number of the average number of observation for that part of the sky. So far there have been 3 data releases. So there was DR1 in 2016 where we released only the position and the G magnitude, and for I think was about 1.4 billion of stars. And then a few years later, in 2018, we published also the color of the stars. So yeah, there is the famous Milky Way map that made by Gaia that now is kind of iconic. And yes, I'm arriving to DR3 in 2022 when we released the, of course, sorry, forgot to mention that in both in 16 and 18 we released also the astrometry, so also the parallaxes and the proper motion, not always for all stars, because there were some selection cuts done, but going through the releases, the number of observed objects increased, the data quality improved because we had more data, we had improved the calibration and so on. So up to DR3 in 2022, when we released again the astrometry and the photometry, but also the radial velocity. And so here the plot on the right, you have the different map of the galaxy. So the top one is basically the radial velocity. The second one is the radial velocity plus the proper motion. So really this shows you how the stars are moving in the Milky Way. The third one is actually the interstellar medium maps. So you can clearly see the interstellar medium clouds. And the last one is the astrophysical parameters obtained by the spectra. So we can do the chemical tagging from on the Gaia, on the Milky Way stars. One thing that we also published was the spectra, so both the RVS and the BPRP spectra. So that was we released, I think it was 200 million of low resolution spectra. That was the big things in Gaia, in DR3. And yeah, so Gaia had, as I mentioned, a science impact on almost all astrophysics fields. So starting from very close to us, so from the solar system, DR3 included more than 150,000 solar system objects. And for this, also the astrometry was very precise, much better than because of the time span of the observation and the accuracy of the instrument, and is much better than any ground-based observation of asteroids. From of course, having a good astrometry allows us to predict better the orbits of these objects. From the spectra, we can measure the color and the composition of these asteroids, and the photometry, the physical characterization. So from the variation of the brightness, we can understand how the asteroids, what is the asteroid shape and how it rotates. And putting all together, then we can distinguish different families of asteroids. For instance, the near Earth, the main belt, Jupiter, and so on and so on. But not DR3 also released not only the solar system objects, but also data for about 30 moons of the planet of the solar system. And another thing that Gaia is great is very useful for instance to help with the ground-based observation of asteroids. For instance, DR3 was very useful in predicting the occultation of what was a Triton. And this helped better the ground-based observatory to plan their observation of this occultation. Another big impact was on understanding the stellar evolution. Here you have a color magnitude diagram created using BP and RP color, and the G magnitude, where you can clearly, doing the selection of stars, you can clearly see the different evolutionary phases of the stars. There have been many things, really, so I'm going just to concentrate on a couple that I thought were among the most interesting. So the first one is the Yao gap. So if we are looking at the color magnitude HR diagram of the red dwarf, this is the plot at the top. And you can see that region between the two red lines, and you can see there is a feature, a kind of gap. And the first, it was a kind of systematic effect, but this actually it's real. It's something that it exists, and it basically marks the transition of the stars from partially to totally convective. So the partially convective stars are the brighter ones, so above the gap, and the totally convective stars are below. The other things that I found quite interesting was the finding different white dwarf cooling sequences in the color magnitude diagram, as the plot in the bottom show. So again, this is an extract from still DR2, I think, and so yeah, you can clearly see the different sequences in the different cooling sequences, and the difference between the stars in the different sequences is the type of white dwarf. So the sequence labeled with H will be DA, so degenerate A. These are white dwarfs that show hydrogen lines, while the B1, the white dwarf of type B are showing helium lines, and you can also see where there is the label with the letter Q, and there is a kind of small horizontal sequence that is mark the region of the white dwarf of type Q, which are the ones that show carbon lines, that are carbon that is being dredged up by the interior of the star to the surface. Yeah, then again, for star another big impact of Gaia on stellar evolution studies is the big catalog of variable stars. And here I'm just going to show some example of the quality of the light curve for the variable stars. For instance, if we are looking at the Cepheids, so it's the plot on the left. You can see the quality of the light curves. I mean, the error bar are even smaller than the point. Other example of light curves are, for instance, the one for the long that have been released in DR3 are the one from the long period, like the one in the top, and I mean that's why Gaia is nice, because it's good because it sampled the sky for a very long time, so we are able to find the periods, also very long periods. And the last one instead is light curve for pulsating stars. And so in the Gaia catalog you can find the catalog of variable stars, their characterization, their period, and other parameters that you might find useful if you study variable stars. But of course, as I mentioned, Gaia's main aim was a map of the galaxies, and so one of the biggest impact was to see how actually is the structure of the galaxies. So again, here you have from DR2. These are color magnitude diagram obtained selecting doing a selection based on kinematics parameters. Here selecting I think the selection was done based on the tangential velocity of the stars, so we can distinguish the population of the thin disk on the left, of the thick disk on the right, and on the halo the thick disk in the center and the halo in the right. And so we can clearly see the impact on the color magnitude diagram give us information on the type of population, and so we can reconstruct which different population are in the different part of the Milky Way. And in particular, if for this diagram, if we are looking at the halo color magnitude diagram, we can see two main sequences, and those are follow-up studies show that the difference between the two sequences, these are two different populations, and the difference is the metallicity of the population. So this means that looking also at the kinematics of these objects, it was found that these two populations have a different origins. And I think this was the start of studying, not studying, sorry, these two sequences basically are thought to be the caused by an event that happened in the Milky Way billions of years ago. That is the merge of the Milky Way information with a galaxy, with the satellite galaxies. And here there is a simulation of this event. The satellite galaxies was this structure is called was called Enceladus, and this nice animation show how the merge happened, and the satellite galaxies was disrupted by interaction with the Milky Way, but we can still see the different origins of the two population in the Gaia data. And so again, one of the big impact of Gaia was finding the stellar population streams. Again, making selection of the kinematics of the stars and analyzing their chemical properties, it was found that a lot of stars in the Milky Way belong to stellar streams that belong to different population and are the results of the merge of disruption of again satellite galaxies of globular clusters. Up to now, there have been discovered more than 100 stellar streams, and these are important because they are gravitational tracers, and they can give us also information. They can help us to constrain also the content of the dark matter in the Milky Way. I found that this. If you want a review of all stellar streams, because there are really many, I suggested Bonacca and Price-Whelan 2024. There are many information also how to use the Gaia data to recover the stream. Yes, a much more recent results is the finding that the disk of the galaxies is actually wobbling. So what does it mean? So Poggio et al. In 2025, this year, selected a sample of stars where I think there were young giants and Cepheids at slightly different distances from the center of the galaxies, and the samples, you can see it in the right figures with different colors, and they measure the kinematic properties of these samples, and the plot on the left show the residuals of the against tangential velocities for versus the distance from the center of the galaxies at different longitude in the Milky Way, and you can see, and then these are actually residuals because from the velocities. We know that the disk is not actually flat, but is warped. So they measure the kinematic properties of these objects. They subtracted the warp, let's say, features, but still they found that there are this kind of wavy features in the tangential velocity residuals, and this is a hint that the galaxy is actually there is some sort of wave going through going through the galactic disk. There is a nice animation as well that show the effects. I don't know. Can you see the animation actually?
Yes.
Okay. Yeah. And so that's just to show that how the galactic disk is moving like a kind of spinning top, wobbling like a kind of spinning top. Another big impact was the discovery of black holes in our Milky Way. So the first two were Gaia BH1 and BH2 found in 2022 and 2023 by El Badri, and these are one is a companion of a sun-like stars, and the other is a companion of the red giant. How do we know that there are black holes? Because we can see it in when we measure the proper motion of these stars, and we fit a model to the stars and to this proper. We fit a single star model to this motion, and it doesn't fit. So there is the dispersion is quite big. It means that the single star model is not the appropriate one. So we try with a binary star model, and that's what was done, and that's how the two dormant black holes were found. In a similar way, also the Gaia BH3, that this was much more recent one in 2024, and that was found orbiting in a binary system with a metal-pooled red giant. And we can see the effect of the black hole on the stars. Well, the plot on the bottom showed the effect of the black hole on the orbit of the thing that we can observe, the stars. So, as I mentioned, the proper motion need a binary star. The binary star model fits better the proper motion, and from this we can actually recover also the orbit parameters of the system, and also, and we can see again the variation of the system from the variation of the radial velocity, and from all of this we can measure again the spectrum for the mass of the black hole. And BH3 was the biggest, the most massive black hole found in our galaxies. This is actually a teeny tiny preview of DR4, because the BH3 was found during the validation of the astrometry, and is actually the data, the epoch data used for the discovery are actually available. They're already public. I left there is a link with to GitHub where there are the data, the epoch data, and also a notebook to retrieve the orbit information. So yeah, therefore, in a way, is already out. So far I talk about so we started from the asteroids, going toward we looked at the stars, and now we can also look outside the Milky Way, because Gaia can observe also outside the Milky Way. In particular, in DR3 was released a catalog of almost 2 million of quasars candidates. We know that they are quasars because it's visible from the spectra. The map show the distribution in the sky of the quasar candidates. I think actually this a bigger selection of what was released. Then the catalog was you have to make some cuts, some selection on the data to be sure that what you are seeing is actually a quasars. And so the catalog of quasars that were released were had a purity of 95%, so they were quite good. And yeah, as I mentioned, you can see them that they're quasar from the spectra, where you can clearly see the emission lines, and from the emission lines, then you can measure. You're able to measure also the redshift. Yeah, and then unfortunately, yes, it was a very sad moment. In January, Gaia stopped observation. So after 10.5 years and 3 trillions of observation, more than 2 billion of stars observed, and really a lot of data, Gaia consumed all the gas. Sorry?
No, continue.
Consumed all the gas, and so the mission, the observation ended. after actually 15th of January, there were still 2 months where a lot of data were carried out to check more, to have a feedback. Some tests were carried out that couldn't be done during the observation, during the mission. And so this was mostly to understand better the satellite and to improve the calibration. In particular, one test that was carried out was trying to understand why the basic angle, which is the angle between the two telescopes, oscillates. I'm not sure that they understood yet how is that. So I think they're still investigating the issue. And finally, Gaia was switched off in March. The top left image show you well, they switched off to one CCD at time, so you can see during the switching off. And before that, actually, another thing that I forgot to mention was that they did this test where they rotate Gaia so that the sun shield was facing the sun. So Gaia was very, very bright and was visible also from ground. And that the right bottom image showed the path of Gaia in the sky when it was visible. After it was switched off, Gaia was put in orbit around the sun and should stay there for at least 100 years without the risk of it falling to the earth. So we should be safe for 100 years. As I say, end of observation, but not end of the operation. Operations are still continuing. We are, again, still in operation for DR4 because data are still being processed and validated, and DR4 is expected at the end of next year, and is basically the nominal mission based on 5.5 years of data. But then there is a DR5, which is expected not before the end of 2030, which is basically the extended mission and double the data. And so these are still Gaia mission operation. And then, I'm going to talk later on about Gaia NIR. I'll just go on with the data release first. So data release 4 will contain a lot of data. So there are going to be a consolidated Gaia source table. The Gaia source table is the table where there are the mean data, so the astrometry, photometry, astrophysical parameters, all the mean data for 2 billion sources, and this is the consolidated one. And the radial velocity, and there are going to be also published flags that will help the users to understand better the data, to understand which one you can use for carry out certain type of study and so on. Again, there are going to be also the astrophysical parameters, both the mean and the epoch. So the epoch are the single observation, the mean, of course, are the mean. There are going to be also data from selected crowded fields. So these are some globular clusters and I think also a region in the body window. And these are special data because they've been observed not in the nominal Gaia data, but with in a special way. Is actually the only time when Gaia could take images. And of course, since it couldn't do it for all the sky, but only it could do it only for a small selection of fields, and it was decided to do it for the crowded fields where it is more complicated to process the Gaia data. And again, there are going to be extra galactic tables with the galaxies, gravitational lenses, and quasars. And also data for non-single stars, so data for binaries and other things. But the most important, and of course also solar system object. So this is what's going to be published. The most actually no, what's in the thing that is more interesting and is that there are going to be the epoch data for everything. So the epoch astrometry, the epoch photometry, and the epoch spectra. So you are you could wonder if it's therefore other than okay, having the mean and the epoch data, but are the uncertainty better? So is therefore going to be better than DR3? And the answer, of course, is yes. Here you have the astrometric uncertainty on the mean value for the parallax and the proper motion, and you have the comparison between DR3 in orange and DR4 in blue. And well, for the parallax, you see that it scales, of course, it improves, well, the calibrations are improved, but just because I use many more data, the uncertainty scales with the square root of 2 with the number of observations. And the improvement was even greater than expected for stars brighter than G13. And for the proper motion, we have a similar, similar improvement, but actually is reached for all magnitude, also for the fainter stars. So uncertainties are better, but also the quality of the astrometric solution is better, because a problem that Gaia had in the past was the presence of systematics in the residuals. Here you have a comparison between the residuals in the parallax in DR3. In the left plot, you can see all these this pattern. This is caused by systematic, and improving the calibration model and trying to optimize in a better way all the calibration model, things improved a lot. And in fact, well, you should compare Gaia DR3 and the plot on the left and the plot on the right. You can see that there are no more patterns, meaning that the quality of the solution improved. So, well, you could wonder what to do with the epoch photometry. The point, well, in general with the epoch data, is that you can actually, if you think that the DPAC haven't done a good job, you can actually try to find a better astrometric solution. You can actually, I don't know if you have your favorite stars, you can try to apply a different transit selection to change the source model. For instance, if it's a binary or a single stars, you can basically do what you want. And of course, also sorry, this one are actually the astrometric uncertainties on the mean, publishing also the epoch astrometry. Of course, there are uncertainties also on the epochs. And here you have a comparison. Well, the blue line corresponds to the formal uncertainty per CCD. And this, well, is quite good. It's around 50 microsecond at a magnitude brighter than 13. This is per CCD, so basically per every observation. But if every time, well, one thing that I forgot to mention is that when a star is observed in the astrometric field, is observed 9 times in the 9 CCDs. So if you average over these 9 CCDs, so per transit, then the epoch astrometry uncertainty improved to 15 micro arc second. so these are the formal errors. Of course, we try our best, but there are still the calibration are not perfect. But still, even with some moderate errors, we reach an accuracy in the in the epoch astrometry of about 20 between 20 and 150 microarc second. Another things that will be published is a list of candidate of stars with exoplanet. And because yes, you can, which is this is going to be a sample of 10 to the 6, 10 to the 7 stars, which is unbiased across the spectrum. So for every spectral type, age, and chemical composition. And it is predicted that we are going to be for the stars the astrometry is going to be published. So also the candidate the candidate planet mass and semi-major axis are going to be published, and is yeah, I mean, this will help scientists to increase greatly the number of planets of exoplanets. And these are considering, for instance, if we take giant planets with a mass smaller than 15 Jupiter masses. So yeah, the prediction is that 1,000 will be found, and this is considering only the nominal mission. If we look at DR5, which is a even longer time span, this number could triple. And yeah, here there are some example of the XP spectra. Well, in black is the XP spectra for the standard stars that are used to calibrate the Gaia data. In black are the externally calibrated spectra, and in yellow higher resolution spectra. So you see that there is quite a good agreement, and you can see that there are very many different stellar type. It is important that Gaia is calibrated using a wide range of spectral type stars, because the calibration needs to be homogeneous across all wavelength range. Okay, so the photometric uncertainties again is going to improve for DR4. This plot shows the error versus the mean G magnitude across the different release. In this case, well, the gray lines, the one with all the yeah, the gray line basically represents the photon noise, and the errors in this case are scaled to a single CCD transit to show the improvement in the photometric processing, so that the uncertainties scale, since the uncertainty scale also with the number of observation, scaling to one single CCD transit, as I mentioned, show the improvement in the processing. And I mean, we are reaching the photon noise limited for some of the stars. And also the epoch radial velocity are going to be published for the bright sources. So with the magnitude G in the RDS brighter than 14. And what you can see is, well, here I just show an example of time series for a Cepheid, and you have in the bottom plot there is the variation in the magnitude, in the G magnitude, while in the top plot there is the variation of the radial velocities, and these basically shows the the pulsation mode of the stars, so that can be characterized quite well. So this is for the bright stars in RVS. Of course, there are going to be also the faint stars. The faint stars are really faint, and the signal to noise is quite low, typical lower than 1. And well, here you can see is well, the red line is 0 level, and the blue line is the continuous of the spectrum. So you see that I mean, well, you can see that there is a lot of noise, but nevertheless, there are lines. To convince you of that, here, well, this is just for illustration purposes. It's not something that will be done in processing, but just to show you that these 6 million faint stars combine, and you can see, well, here there is also the comparison with a higher resolution spectrum. You can see that it's clear that there are the much weaker lines are visible. So in the processing, this will come out. Then other things that are going to be published is the parameters of the orbits for both components of resolved binaries and also the orbits for triple system. And then yes, also Gaia observes not only stars but also extended objects, and so as I mentioned before, galaxies and quasars, and also surface brightness profiles for some of the brightest object. And another thing that is going to be improved in DR4 is about the gravitational lenses. So also in DR3 there were candidates of gravitational, has been identified gravitational lensing events. In DR4 this is going to be more robust, including outlier rejection, and also checking that the spectra of the lensed object are similar. Here in this plot you can see the images show you the lensed images, and in the two small panels there are the mean spectra of the objects of the lensed object, and looking at the spectra, they are indeed quite they're similar. Again, well, going quickly because I think that don't have that much time. The number of asteroids is going to improve. DR3 was 150,000. Here is more than doubled, and with quite good quality. And also the processing of the source image object is improved, because here in this plot you have the reflectance spectra in BP and RP. The reflectance spectra is basically obtained comparing the spectrum of the asteroids with what is called with a solar analog. So basically from the difference of the spectrum of the asteroid with one on the sun, we can understand the chemical composition of the object. And in DR3 there were some problems, especially in the red part, that improved. You can see that the black dots, which are Gaia DR4, agree better with other catalog observation, and also in the blue part of the spectrum is much more extended. And another thing that is going to be published is the taxonomic classification of these asteroids, but also for some subset of these objects, also the shapes, how these asteroids spin, and also the coordinates of the poles. So summarizing, well, Gaia DR3 is going to contain 2.4 billion of sources. So DR3 was just a bit less than 2, so half a billion sources more, which basically correspond to 142 billion detection. And there are going to be, say, time series for all type of data. So from the astrometry, and that can be used for the orbits. To distinguish, for instance, as I show you, to find black holes or to find binary, better characterized binary system, and so on and so on. For the radial velocity, to better characterize variables, and yeah, better from the photometry time series characterize the variables. From the spectroscopy, from the low resolution spectra time series, well, again, we can understand a lot about the stars, seeing how the spectra varies with time. And so finally, DR5, which is expected at the end of not before the end of 2030, and it's going to be based basically on double the data in comparison to DR4. And here, well, basically is the plot on the right show you the expected accuracy of the objects for three type of population, which are the tip of the red giant branch, the horizontal branch, and the main sequence turn-off. And so showing that with the doubling the time span, the length of the mission, we can go deeper and fainter. For instance, just if you want to have a very good catalog, so selecting for instance, the uncertainty of the proper motion, you want uncertainty smaller than 5%, and you see that Gaia nominal you can reach only certain magnitude and only certain distances, while with using with the Gaia extended mission, which is the red line, you can go again deeper, much deeper, and fainter. And if you are not picky and you are happy with an uncertainty of 50%, again, you can go even deeper than that. And yeah, finally, well, yeah, Gaia is limited in the galactic plane and the galactic center because of the interstellar medium. I mean, yeah, on the left there is an image that I showed before of the interstellar medium maps made using Gaia data. So this problem can be solved going into the infrared. The plot, the image on the right show the increase in number of star observed going from infrared, from visible to Gaia. So it's the ratio between star observed in infrared and stars observed in Gaia, and you see clearly that the improvement, the great improvement in the galactic plane. So the proposal is to make another Gaia but in the near infrared, in the RJHK bands, and this will allow us to observe more than 15 billion stars in the disk, bulge, and bar, and down to magnitude 23, 24. Gaia now, I think the limit now is 22, so at least 2 magnitude deeper. And of course, we can combine the data from the two surveys and reaching an accuracy in the proper motion down to sub-micro arc second per year. And these are the current design is a kind of similar to Gaia, so with a big focal plane with different detectors devoted to different instruments. Again, we have a very wide and infrared band for the astrometry and different bands for to obtain colors and low resolution spectra. And again, well, the idea is to have also like, well, we need to have also the radial velocity. So also a high resolution spectrometer is considered in the project. So there is going to be a paper from by OBS Tallinn preparation, I think soon. And I mean, until a few years ago, this was considered unfeasible because there were no infrared detector working as a Gaia CCD, so in TDI mode. But luckily there's been a lot of progress in technologies, and now yes, there are these avalanche photodiode arrays, APD, that work. They can be read with a very high frequency, so mimicking TDI mode, and with a very low readout noise. Of course, since Gaia, we are talking about infrared, and we are going to observe a crowded region. In infrared, the PSF is going to be wider, and so crowding can become quite difficult to crowded fields can become quite difficult to process. So the idea that has been explored now is increase the size of the mirror. And so to up to 3 meters, just for comparison, Gaia mirror is about 1.5 meters, so double in the size. And here just expected performances comparison between Gaia after 10 years and the performances expected for the Gaia near mission using a Gaia-like mirror and a much extended and a bigger mirror, and we can see that we can go much deeper and with a better we can observe all the reddening stars with a better precision. Finally, this is what Gaia mission in a nutshell. What I haven't said yet, again, who. So all these things have been done by the Deepak, all the Gaia data processing and analysis have been carried out by the Deepak consortium, which I'm a member. Here there's a picture of most of us made during the last Deepak plenary meeting in Cambridge a few months ago. And so if here there is a request, please, if you are going to use the Gaia data, and please cite the data release and the processing papers, because this will help us in requesting the fund, the fund from the funding agencies. Without funding, we cannot really carry out the processing, and there is not going to be further data release. And I think I finished.
Thank you. Let's okay, Giorgia, unfortunately we've run, and there's another class coming, so we have.
I'm sorry.
Without asking questions, but there was one in the chat.
Because where is the chat?
Yeah, no, it's okay. So anyway, thank you very much for coming, and we sure learned a lot. Yeah.
Okay. Thanks for inviting.
Bye.
Bye.